Hello, my name is Shruti Vinod, and this is Lab Report 4 for Physics 2212. So the purpose of this lab is to measure the distance dependence of a magnetic field due to a small bar magnet and compose measurement of distance dependence using the Biot-Savart law. The principles involved are magnetic fields, Biot-Savart law, magnetic field superposition, and bar magnets that we take as acting as magnetic dipoles. And the overview is that there was a correlation in the order of magnitude between the computational and experimental solutions for the net magnetic field. So as we can see here, we have the main physics ideas, which is materials involved or used is Tesla meter, bar magnet, lab 2 spreadsheet, which was provided to us, pieces of tape, and ruler, meter stick. And relevant formulas are the distance-dependent formula, Biot-Savart law, and how to measure the magnetic field of a dipole. So here we can see that the experimental setup involves the system, which is a magnetometer, surroundings, which is bar magnet and earth, and initial conditions are that the X component of the magnetic field is 0 Tesla. So here we have the data on the distance measurements for different magnetic field strengths. And also to the right, which is the graph, we have the linearized plot of the averages. Now, based on the line of best fit, we can determine the variables n and k. And our next scenario is the off-axis magnetic fields. This procedure is similar to what we did for an on-axis magnetometer, up and perpendicular to the direction of the axis, and the XYZ components of the magnetic fields at a perpendicular scenario, or at a perpendicular distance. And based on the calculations, which is using our N and our K, we can find what mu is, and our mu is determined to be 3.206 amperes meter squares, or Newton meter over Tesla. So there were 4 questions that we were asked to answer, which is when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This was determined to be true. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. This is false. The position of the magnetometer has no effect on the measured x components of the magnetic field, which is false. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, which is true. Next, we have the coding section, and I'll describe each part. So the first one was we had to put in the magnitude of the magnetic moment that we derived. And then the second one is we created a function for the magnetic field, which is the one on the right. And then third part was visualizing the magnetic field on axis. And here we have the distance, which is this value determines how far away from the origin in meters the arrows will be placed. And then fourth, we have observation locations that we determine. So there are 2 on axis and 4 perpendicular to the axis. 5 we have to draw 2 arrows to represent the magnetic field on axis, and so we determine that. And then 6, we have to draw 4 arrows to represent the magnetic field perpendicular to the axis. And then finally, we are trying to visualize the magnetic field 45 degrees off axis. And this involves putting in the average distance perpendicular from whatever we get from the experiment or the data. And then we finally have to draw arrow to represent the magnetic field 45 degrees from the axis. And here are my results. We have the B on axis, B perpendicular, the distance, and B at 45 degrees at a distance D. So in conclusion, the computational result for B net at 45 degrees off axis was 2.8 for e to the power negative of 5. Experimental result, though, was 5.52 e to the power negative 5. So here we can have sources of error, which is like human error, shifting phone when taking measurements, or like rounding errors. And location could also be an error, which is other objects could have interfered with the magnetometer. So what if? What if we hadn't oriented our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? How would this have changed our results? So if we had oriented it, we originally had oriented X hat to magnetic north to calibrate 0 Tesla. If this was oriented incorrectly, the Earth's magnetic field would have interfered with the bar's magnetic field and skewed our result. So the second one was, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The magnetic field magnitude calculations would have increased, which is doubled, but the direction would have stayed the same. Thank you so much.